Hi, everyone. I'm Laura Kay. I'm chair of the Department of Physics and Astronomy. So welcome to Barnard if this is your first time, and if you're alumni, that's great to come back. Our speaker tonight, Janna Levin, is also an alumna, and when she was here as a student, she studied physics and philosophy. I first heard her speak at Columbia some time ago, and when I heard her speak there, I thought we got to get her back to Barnard. She's currently the Tau Professor of Physics and Astronomy at Barnard College, and has contributed to an understanding of black holes, the cosmology of extra dimensions, and gravitational waves in the shape of space-time. She's also Director of Sciences at Pioneer Works in Brooklyn. Her previous books include How the Universe Got Its Spots and a novel, A Madman Dreams of Turing Machines, which won the Penn Bingham Prize. She was recently named a Guggenheim Fellow, and she's going to talk about her latest book, Black Hole Blues and Other Songs from Outer Space, which tells the inside story of the discovery of the century, the sound of space-time ringing from the collision of two black holes over 1 billion years ago. So I'll give you Janna.
Thanks everyone for coming. I do want to talk about this discovery. I'm curious, how many people heard in February the announcement of the discovery of the collision of two black holes and the ringing of space-time? How many people heard about this, the gravitational wave discovery? How many people about an hour later thought, yeah, I don't get it? Okay, I know it was more of you that are confessing. What I want to do tonight is to kind of pick apart what that discovery was about and why it was so monumental and so exciting. Thank you. Okay, sorry about that. So when LIGO made the announcement, LIGO stands for Laser Interferometer Gravitational Wave Observatory. It was a fairly obscure experiment on February 11th of this year. Very few people had heard about it, and yet that morning, every major newspaper in the country and internationally featured, I was sitting next to somebody from the New York Times who had his finger hovering above the send button, right? They had already written their articles and they were just waiting for confirmation and the full announcement. Featured this discovery, calling it the discovery of the century. And yet nobody had heard of this experiment. One of the myths is that this instrument just turned on and made a detection and it was so wonderful. The people who worked on this campaign worked on it for over 50 years. It was an arduous, arduous campaign. There was a lot of moments, precarious moments where the experiment almost failed or wasn't built. And there was a lot of community opinion against them. A lot. And so I really wanted to tell this story, and I happened to be writing the book over the past couple of years, but even at the time that I submitted my draft of this book, the experimentalists were telling me, oh, there won't be a detection until 2018 or 2020 at the earliest. These are people on the team. So this discovery took them by surprise as well. So let's talk about what was actually discovered. 1.3 billion years ago, two black holes collided somewhere in the southern sky. We don't know where exactly. It's hard to locate, and I'll describe why that's the case. Since that time, they created what's called gravitational waves, which are waves in the shape of space-time, and we'll pick apart what those are exactly. And they emanated through the universe, taking their time to finally get here. They travel at the speed of light, but they are not light, finally sloshing over the Earth and being recorded by this very ambitious instrument. And so when they made this detection, they played it back as sound. Have you heard the sound? Those of you who heard about the detection heard the sound. So I'm going to play it. They're going to play twice because there were two instruments that recorded it. And one literally in the frequency it was recorded, and then it's going to play twice again, shifted up in frequency in a way that's more friendly to the human ear. So let's listen to the first recording. And then they're doing it again. I don't know why. They just like doubles. They just kept doubling it. So this was released by the LIGO team as the detection. It is not a picture of the sky. It's something fundamentally different. It's a recording. If you think of the black holes like mallets on a drum, they ring space-time like a drum. And that wave in space-time is what was recorded, as though the drum was ringing so quietly that you needed to build a sensitive detector to measure the waves and the shape of the drum. And we'll pick that apart, and it plays it back to us as sound. The experimentalists literally listened to the detector in the control room. So let's go back to the beginning and understand why this was such a huge discovery. Very nearly everything we know about the universe comes to us from light. Very nearly everything we know comes to us from light that has traveled sometimes from 45 billion light years away and tracing back to the origin of the universe 14 billion years ago. If we look up in the sky, this is taken from the European Southern Observatory in Chile, just with a digital camera. If you hold your eyes open for a very, very long time, this is what the sky would look like. This is our Milky Way. This is a picture of our own galaxy from our position bound to this Earth. And the reason why we know what we know about the universe from light is because we really are bound to this rock. If we take a bigger view of the Milky Way, this is a real map of our Milky Way taken with all the observations that we've collected of what the galaxy looks like and placed them spatially where we believe these observations to have originated. And if we go into the plane of the Milky Way, we look around at these hundreds of billions of stars in our own galaxy, and we find this one pretty average star, a nice yellow star. It's our sun. They have to tune down the brightness so we're not blinded by it. And we come to the sun and we see our solar system. And there we are, famously, the third rock from the sun. And we have gone to the moon. I mean, that is tremendously exciting. But if you think about where we've traveled physically off the Earth, it's just nowhere in the cosmic scheme of things. Nowhere. So we can't go and explore space, at least not yet. All we can do is receptively receive the light, and here we are on this blue planet, and that's what we're doing. And you see the view of the Milky Way looks the way it does because we live in the plane of this galaxy. We can't send probes to go look at the Milky Way from above. We're nowhere near that technologically. I know some of you might have heard about the Mars mission, which just recently, we think, crashed into the surface. You know, space is hard. I forget which astronaut it was who was looking out the window recently when one of SpaceX's what's it called? The delivery missions, supply mission blew up. He could see it out the window of the International Space Station, and all he said was, you know, space is hard. It really is. He had to wait another month for, I don't know, strawberries or something. Voyager, which was a spacecraft that was launched in the 70s, is the first one to really break out of the sun's magnetic influence. It's the first spacecraft to sort of become interstellar, and traveling to the nearest star system at its current speed would take 35,000 years, right? So this is where we are, and what we've done with this limitation is actually tremendous. This is called the Sloan Digital Sky Survey. Again, it's not a cartoon, it's real astronomical images. Every image in this survey is an entire galaxy. So our Milky Way has 100 billion stars, or a couple hundred billion stars. Every galaxy that we see probably has 100 billion stars or more. And there are as many galaxies in the observable universe as there are stars in the Milky Way, which is to say, even just the distance that we can see, hundreds of billions of galaxies. Okay? And it's a spectacular movie that we've built or composed of the history of the universe going back to the Big Bang 14 billion years ago. It's tremendous what we've been able to do from this little rock bound to it. And yet it's a silent movie. Right? It's a silent movie that we've composed, frozen snapshots dating back as far as we can take and as far away as we can see. And so this observation by LIGO, for the first time, was an observation in something other than light. I mean, we get particles too, so I don't want to be too extreme. We get cosmic rays and particles and neutrinos, but this is the first time that something as purely gravitational, without receiving any light at all, has been detected. And I just thought, you know, since this is a science lecture, sometimes I don't like to go into this part, but I thought it would be kind of fun to talk about the deeper theory or how this idea came about that gravitational waves even existed. And of course, it goes back to Einstein. I know a lot of the papers said things like, scientists prove Einstein right. Einstein was not as concerned as other people are about being right. I mean, people were more concerned about him being right than he was. When he first started to talk about gravitational waves, these waves in the shape of space-time, it was right after he wrote down his greatest idea, published his greatest idea, the general theory of relativity. And he immediately turned to this problem. Can there be waves literally in the fabric of space-time, curves that squeeze and stretch space and oscillate and move through the universe? 20 years later, still did not know the answer to that question. He kept changing his mind. He would write papers saying they don't exist, they do exist, they don't exist. This was a deeply, deeply difficult problem. At one point, he wrote a paper saying they do not exist. It was accepted for publication. Between acceptance and submission for print, he put in another paper that said that they do exist. And somebody said, Einstein, you have to be careful. Your famous name is going to be on these papers. And he said, oh, my name is on a lot of wrong papers. I mean, it wasn't his first concern. So when asked in 1936, so do you think gravitational waves are real or not? He said, I really don't know, but I know it's an important question. And so let's get to why they even come up in the conversation. It's kind of fun just to think about gravity at all. And this is really what Einstein's general theory of relativity you should think of is interchangeable with a theory of gravity. Okay? And you should think of that as interchangeable with a theory of space-time. That's what he did. So how does he get to this conclusion that gravity is space-time? That's the point I want to make right now. So here's how he starts. He says, let's say I want to think about gravity, and I'm standing in an elevator, or you're sitting on your chairs. We think of gravity as feeling heavy, right? Feeling the weight in my feet, feeling heavy in the chair, lying in bed and feeling heavy at night. He says there's something wrong with all of these examples of our experience of gravity, and that's that something else is required and in the way. In the case of the elevator, it's the floor of the elevator. In the case of sitting in your chairs, it's the chairs. In the case of the bed, it's a bed. Why do I need these things in the way to discuss pure gravity? So he says, imagine I'm in the elevator and I cut the cable. Let's get rid of the elevator somehow. Cut the cable. Now you're experiencing pure gravity. No longer the atoms of the elevator interrupting this pure experience. So what happens if you're in the elevator and the cable is cut is you go into what's called free fall. You begin to fall freely. If you were to wake up, I don't know why you'd be unconscious in an elevator, that's your business, but let's say you wake up in the elevator and you're falling freely, you would not know if you were floating in the International Space Station or you were falling around the Earth. You could not tell the difference. This was what Einstein called his happiest thought. It's called the equivalence principle. If I literally fell in this elevator, I could let go of the microphone and it would float in front of me, like I was in the International Space Station. I could pour water droplets and drink them out of the air. And this simple thought experiment, this observation that gravity is not heaviness, gravity is actually weightlessness. It's falling as freely as possible in the presence of something like the Earth. And one more step, and he's going to get to curved space-time. This is a demonstration of free fall. This is a couple of really silly artists who are also friends of mine, so I'm allowed to say that about them. If you liked early punk rock, that's Jem Finer on the right, who used to be in the Pogues. You're right. Asaman Baswat, both British artists, they went to Moscow to do one of these parabolic flights, fondly known as the vomit comets. What they do is they're not in outer space. They're just in a plane in the Earth. The plane goes up, and it goes up high enough that they do a nosedive. So they're basically in the free-falling elevator. The cable's been cut. They do a total nosedive. And while it's nosediving, they're in complete free fall. They might as well be in the International Space Station. The astronauts in the International Space Station aren't weightless because there's no gravity. They're weightless because the space station is falling. It just always clears the surface of the Earth. It never crashes into the surface of the Earth. So this would be, this would end unhappily. They're pretending to be genies, I guess, obviously. In like a couple of trips later, so what it does, it free falls, and then, because it doesn't want to avoid a collision with the Earth, it scoops back up again. And when it starts to scoop up again, you get the real feeling, what the plane is doing is it's interrupting their free fall. It's stopping gravity from doing its natural thing. So here you see right now the plane scooping up slowly, and in a second, they'll be pinned to the floor, just like you feel like you're pinned to your chair, or you're pinned to the floor of the elevator or your bed. And I'm pleased to say that in one of the subsequent flights, they actually got onto the carpets. I was going to show you this video, but I'm going to skip it. Does anyone know the band OK Go? They also did a video in the Vomit Comet. It's pretty fantastic. But well, okay. Do we want to see it? Yeah, why not? Okay, let's see it. It might be a little loud. Let me see if I can. If you can ride the volume. Louder. Okay, in a second, here they go. So while they're free falling, they might as well be in outer space. We'll just go to the end of the second because it's pretty great. Apparently they did 52 flights and everybody was throwing up by the end of it. But if you haven't seen the whole video, it's really worth seeing. It's really spectacular. Okay, sorry, I'm going to pause there. Okay, I could watch the whole thing. I could just sit down in a chair and we could sit there and watch it. So why is this idea of free fall so important? Why does Einstein call it his happiest thought? Because from this one thought, he says, well, if I see how things fall, I can understand something about the space around it. So let's look at the Earth. Let's forget the Earth. Let's look into empty space. Suppose I'm an astronaut floating around in empty space, and I take my remote clicker and I throw it. You know, what's going to happen to it? It's just going to go off in a straight line. Okay? That's what we mean when we say space is flat. Okay? We mean that things fall freely in the absence of any other intervention along straight, flat lines. Okay? But what happens if I put something like the sun in space, in the universe? Einstein reasoned that the sun must curve space-time, because if we look at what happens, let's pretend it's the Earth. If we look at what happens, were I to throw this, which I'm not going to do because it's brand new, were I to throw this in as straight a line as I could, is it going to travel in a straight line? Wouldn't you be surprised if it just kept going in a straight line? Okay, what does it do? It falls on an arc. And Einstein reasoned that if I throw probes all around the Earth, I can trace the curves in space-time that are created by the Earth. Because when something falls freely, it is tracing gravity in its truest, uninterrupted form. It's brilliant, right? Now, that intuition is tremendous, and I don't blame you if it slips away while you're falling asleep tonight. You know, it takes many, many years to get a handle on it, but it took him at least a decade more to mathematize it. It was still a long, arduous process to understand the core mathematics of how to make that relationship. How does mass curve space and time, and how does mass fall along the curves in space-time? But once you begin to think, oh, if things fall freely and they follow curves in space, that kind of makes sense. That's why the Earth orbits the sun on a circle, because it's falling freely. The sun's not touching the Earth, it's not grabbing the Earth. The Earth is falling freely along a circular curve created by the sun in space-time itself. And why does the International Space Station, why do they look like they're falling? Because they are. They're falling freely on a curve that's a circle around the Earth that the Earth created in space-time. And the trick for the International Space Station is that they have to be falling in just the right way, that they're on the curve that never crashes into the surface of the Earth, right? They're on the curve that always clears the horizon. I was talking to an astronaut recently, and I was asking, do you feel like you're falling? Like, because literally that's what's happening. And they say every once in a while you have this sort of sense of it, but it's different because the air is coming with you. The air is falling with you. So it's a different sensation. Now, once you have this idea that there are curves, extreme things can happen, things like black holes. So right when Einstein publishes his general theory, he gets a letter within the year from a physicist named Carl Schwarzschild, who's writing him from the Russian front during World War I, and where he was calculating ballistic trajectories. He was reading the proceedings of the Prussian Academy of Sciences, as you do when you're in a trench. And he came up with the solution of what we now call the black hole. It was not called a black hole at the time. It was 1916. Einstein gets this letter, goes into correspondence with Schwarzschild, and he's amazed. Schwarzschild came up with a solution that describes a curved space-time around an object that's so compact and dense that not even light travels on straight lines, not even light travels on subtly curved lines. Even light ends up in circular orbits at some point. And at some point, when light gets too close to this object, there is no free fall path leading outwards. Even light falls inward. Light cannot escape. And that's what we now call the black hole, an object that is literally so dark, it is the absence of light, it neither emits nor reflects light. And it allows no light to escape. This is a portrait of a black hole. That's the artist's interpretation of the black hole. That's the only cartoon in the place. Okay, so what does a black hole look like? This is not a cartoon. This is a computer simulation of what it would look like if some evil genius was to turn the sun into a black hole. So if you take the sun and you take all of its mass and you crush it enough, eventually the curves in the space-time become so extreme that it leaves a shadow behind it as it collapses. And then the material continues to fall, leaving the shadow behind like an archaeological record. The sun would be, if it were a black hole, 6 kilometers across. It would fit in Central Park, at least. Central Park 6 kilometers across? No, that's not right. Well, anyway, it would fit in Manhattan. All we care is that the New York reference can be somehow employed. So you take the sun and you crush it to 6 kilometers and you have a black hole. This is an artificial Earth because actually, if the sun were to collapse to a black hole, one interesting thing is, I want to dispel this monster black hole myth, is that our orbit would be just fine. The black hole from such a huge distance that we keep from the sun would curve space-time exactly the same as the sun does, and we'd be on exactly the same orbit. It would be completely fine. It would be apocalyptically dark, and that would be bad, but our orbit would be fine. So what Andrew Hamilton has done, who's the physicist who made this computer simulation, is he imagined making a self-illuminated object. This object has to be very small because it's very close to this 6-kilometer-long object. He made it look like the Earth. And you see that as it orbits behind it, that even the path of the light gets bent so that the object looks distorted. It's not actually physically being distorted. It's still a sphere when it goes behind, but it can't hide behind the black hole because the light sprays around and its path gets bent towards us, as opposed to moving just away from us. So instead of it being invisible when it hides behind the black hole, we can still see it. Now, there's no black hole in the universe that we can see like this. Okay? To literally technically see a black hole, we'd have to have something bright behind it and see the shadow that's cast. That's the best that we can do, is see the shadow that's cast. But black holes are tiny. Even if something was 30 times the mass of the sun, it would only be a couple of 100 kilometers across. And we're talking about astrophysical objects that are so far away, there's really never been the opportunity to see anything like a black hole in pictures. If we were so lucky as to have a black hole between us and the Milky Way galaxy, this is what it would look like. You would see the Milky Way galaxy, but it would be distorted, again, because of the path of the light. If you were an astronaut falling into this black hole, and you didn't study astrophysics properly, and you're like, hey, what's that? This is what it would look like to you. Notice of the swirling. The swirling is because in this simulation, we're actually orbiting. So the swirling is due to our own motion. Right now, we've crossed into the shadow of the black hole. There's nothing there. It's completely empty space-time. People think of a black hole as a dense crush of matter. The matter is long gone. What happens to it, we don't know, but it's long gone. It falls into the black hole's shadow and realize that it's bright on the inside. even though it's dark on the outside. It can be bright on the inside because all the light from the galaxy can fall behind you and catch up to you if you're orbiting around. And what you would see is this bright blast of light as millennia passed for the galaxy while you had a few microseconds to live. This is another image of what it would look like. You know how when you concentrate colors, it comes out white. So as the colors of the stars and the images in the Milky Way galaxy get focused onto this ill-fated astronaut, it looks like this big, bright flash of light. So right before being crushed to death in the singularity, the astronaut sees what I call, it's like a light at the end of the tunnel, or a near-death experience, but it's a total death experience. So we don't want to actually do that experiment. We can't do that experiment. Nothing is close enough. But what can we do? We can look for gravitational waves. So I want to emphasize that we think that there are about a billion of the stars in our own galaxy will eventually form black holes. We know that there's a supermassive black hole at the center of our galaxy. It's millions of times the mass of the sun. It's 26,000 light years away, and it's millions of times the mass of the sun. And technically, we're orbiting that black hole. And if we make the same estimate for those hundreds of billions of galaxies, there are a lot of black holes out there, right? And a lot of them we simply can't ever see. We do indirectly see black holes tearing down other stuff on their effect that they have on their environment. But this is really the idea of what could we do without light? What could we do with this completely dark, dead star that we could not do with light? And this is where Einstein started to think about gravitational waves. He said, look, if something moves, the curves it creates in space and time must have to follow it, surely. And how can they follow it? They have to kind of move like a wave. And so he proposed this idea of these gravitational waves. If things bang around on space-time, all those curves must start to move and wave and oscillate. And that was the whole debate about gravitational waves. So this is another computer simulation of two black holes colliding where they have helpfully painted for us the modulations basically in your free fall curves. If that's too abstract to think about, you could say a squeezing and stretching of space. If you were floating nearby, you would literally be squeezed and stretched. And you could also kind of bob on the wave, like something floating on an ocean wave that was ringing. What happens is those two black holes, it was predicted, would collide, forming a bigger black hole, and that these waves in the drum of space-time would emanate through the universe. So, sorry, let me restart that. This is actually from my group, at Columbia and at Barnard, where we simulated what it would sound like. And lots of groups do this. Lots of groups simulate what it would sound like. Now, why would I say what it would sound like? Because if you were an astronaut floating close enough to this banging mallets on a drum, let's say two black holes are orbiting, technically your eardrum could ring in response, even in the absence of air. If you're a sci-fi buff and you get angry when in sci-fi movies, people scream in outer space, and you can say in outer space, nobody can hear you scream. I think that was a byline of a thriller. In this technical case, even in the absence of the air, your eardrum is built, or the ear mechanism is built to ring in response. And this squeezing of stretching in space could literally, at least conceivably, although again, it's not an experiment we're going to do, ring your eardrum. And it happens that these black hole collisions that we predicted were in the human auditory range. You would literally hear it. So I'm going to play for you what the sound of that drum banging sounds like. In this simulation, there are two black holes. I'm painting the orbits here. One is heavy, it's 10 times heavier than the other, so that's painted in yellow. Can we turn the volume up on this one? Thank you. And so it doesn't move as much, but they're both orbiting a common center. The red one is lighter, so it moves a lot. Notice the orbits are really crazy. And if you listen, you can hear literally when the pair points towards us, it's louder, and it gets quieter when it points away. You can hear that as the orbit gets faster, it starts to go up in frequency, and it gets louder. That chirp you hear at the end is not exactly what you expect from two massive black holes colliding, like, I don't know, but that chirp that you hear at the end is very characteristic of black hole collisions. They collide, they form a new black hole, and in their final orbits around each other, they're going so fast, some fraction of the speed of light, the frequency scoops up, and it should start to sound familiar to you about what that LIGO detection sounded like, a little like whoop at the end. Okay, so here, let's fast forward from Einstein to Ray Weiss. Ray Weiss is a young physicist from MIT. He's a young professor at MIT. He started a gravity research program. It's the late 60s. And somebody asks him to teach a class on general relativity. Ray tells me, what I knew about general relativity, you could stick in this finger. And he said, yes. I'll teach the class. I mean, he figures he's got this whole research program in gravity. He can't tell them. He doesn't know anything about general relativity. Very few people did at the time, right? This was not the era where every university was teaching relativity, far from it. And so he starts to teach this class, and he says he was bumbling. He said he was one day ahead of the students at best, but the reason why they weren't walking out was because he kept thinking about ways to make it sound more real, less mathematical. It's a very mathematical subject. And so he came up with this idea. He said, so he hung on to the gravitational waves. He locked onto that. He says the whole damn theory, that was the only thing I could make sense of. And he said, suppose a gravitational wave passes the Earth. How could we know it was real? And he imagines what he calls a haiku. He says, pretend we have these mirrors. So there are mirrors, 3 mirrors in this image, 2 at the ends of that L shape and 1 at the apex. And he says, imagine a laser shines down this L-shaped instrument. If a gravitational wave were to pass, you see how the mirrors are kind of bobbing with the wave because they're in free fall. And they would send the light back to the apex at different times because they're bobbing with the wave and traveling at different distances. And if you could measure that by looking at the light and the interference of the light and the light travel time, you could actually record the shape of the ringing drum. This is very, very similar to how you might record an electric guitar string with the body of an electric guitar. It's actually based on similar ideas. I mean, it's not lasers and mirrors, but the idea is that the string doesn't make the sound until the body of the guitar records the modulation of the string and plays it through a speaker system. And so that's exactly how this little haiku worked, that you could record the ringing drum by building the body of the instrument, and the instrument would play it back to you as sound, even if it was too faint for you to hear originally. This is another image of the LIGO. This is really the deep idea of LIGO. As the mirrors move, they create interference in the light, and by measuring that, that's how you make the recording. So it sounds great. So Ray builds a little prototype. He builds a prototype that's about 1.5 meters in each arm. He builds it in a place called the Plywood Palace, which was this ramshackle structure thrown on the periphery of the MIT campus during the war effort to try to encourage research into engineering. It was meant to be torn down 5 years later. The building lasted 50 years and produced 9 Nobel Prizes. It was as though the crappiness of the structure encouraged this creativity. Ray just said, we were an odd little group in there, is what Ray said. Many people were surprised that the Nobel Prize didn't go to them this year, but there's a whole conversation about that. Probably a 10th Nobel Prize will have come out of the Plywood Palace eventually. And Ray was building it there, and there was this little instrument, 1.5 meters long. He started, this was such an early era. People were still arguing about whether or not black holes existed. They were arguing about whether or not gravitational waves were real. And his colleagues were telling him, you're not going to get tenure. You're not going to get tenure, they're telling him. You're working on nothing important. They said if the sun blew up, you couldn't detect it with your machine. We'd do better looking out the window. And Ray goes, they're right. I couldn't. He starts to do a very long study. We're already fast-forwarding many years. He tries to apply for grants. He gets turned down. Other groups begin to advance because they've heard through his grant application, which they received to evaluate, about this idea, and they start building their own machines in Germany, in Scotland, around the world, and Ray can't get anywhere. And he realizes he's about to lose out on this dream he has to build this recording device. You know, he said, I started life with one ambition, to make music easier to hear, and somehow he ends up wanting to build this like cosmic recording device, and he sees himself losing, and he says, you can't stop people. They're doing a great job too. They're good, they're smart, great engineers, great scientists, and they're doing better than he was. And he said, you know, he thought he was sunk, and then he said, the next big event is that I met Kip. Kip Thorne comes in, he's a famous, iconic astrophysicist, and they begin to push through this campaign together. Kip knows black holes are real, he really believes it, he really believes gravitational waves are real, and he really wants to make this a reality. So by the year 2000, after much opposition, congressional troubles, many failed grants, they finally get the money to build LIGO. In the year 2000, the first generation of instruments are built. They've grown from a team of 2, 3, a handful, to a team of hundreds. The arms, Ray reasoned that in order for his experiment to be successful, that those arms couldn't be 1.5 meters, they had to be 4 kilometers at least. Okay, so these are 4-kilometer-long arms. This part is a cartoon, obviously, but where you shoot a laser down the arms to these stunning mirrors at the end of the 4 kilometers. The mirrors are in things that we call beer chambers. The mirrors, if they ring, if they bob on the wave, just like something floating on the ocean, they send the light back. The light will interfere with itself when it comes back, and you will be able to tell that it traveled different distances along the arms, and thereby record the wave, record the ringing of the drum. So the idea was to put one on one coast, one on another. So one of the LIGO machines is in Louisiana, very near the recent flooding, and the other one is in Hanford, Washington. And they're not correlated, so that they both have to make a recording to have any confidence that something happens. So something happens out in space, whatever, it rings the machines. Not just black holes, but other colliding stars, neutron stars, exploding stars, maybe even the Big Bang. This is what the instrument sounds like if you're in the control room. It sounds like noise. And that's because there's a lot of noise. They can hear, literally hear, trucks driving by. They can hear earthquakes in China. They can hear winds off the coasts. They hear planes overhead. The sensitivity of the instrument is such that the mirrors, they have to record movement of these mirrors, which are something like 40 kilograms, over 4 kilometers, of less than 1/10,000th the width of a proton. It is an incredibly difficult experiment, and technologically nobody disputed that they had already, by the year 2000, done something technologically great, but they hear nothing. They hear nothing. They run several science runs and they hear nothing. They're not that surprised. They often proposed a second generation of machines would be required. But by now, you know, community opinion was already pretty against them. Didn't think this machine was worth it. It's now got a price tag of $1 billion. 1,000 people are working on it. And they're building a second generation of machines. And there's a lot of opposition and a lot of negativity. And so when I was following, I'm a theorist. I work on very theoretical stuff. I don't build things. I think I became completely enamored of the physicality of the experiment, of the insanity of the ambition. It was like this story of climbing Mount Everest, you know, just trying to get up the mountain. Their bodies along the way. Not everybody makes it. You know, there's terrible stories along the way. But they keep persisting. In August, things like this happen. This is bad. The Hanford machine is on the site of the plutonium separation facilities that were used in the first bombs in World War II, And those separation facilities are now used for other purposes, some cleanup facilities, but they're still active nuclear sites, so they're heavily patrolled. One of the patrolmen was cruising around very fast with a poor knowledge of the local geography in the dark, and ran into one of the arms. I should emphasize that these arms are in a vacuum state. They're two of the largest holes in the Earth's atmosphere when combined. There's less stuff in those arms than there are in regions of interstellar space. And had he punctured the vacuum, he broke his arm, but not the arm of LIGO. Had he punctured the vacuum, it could have killed him. It's like opening a door on the space station, but the stuff's on the outside and the vacuum's on the inside. And also, when you ask the experimentalists, that vacuum was pulled in 1998. They said we'd all go home. It's over. Okay, that is one of the major challenges of the experiment, is keeping that vacuum preserved. Ray in his 80s is still walking the tunnels looking for leaks, finding leaks because he discovered wasp urine corrodes stainless steel. Who knew? Who knew? So lots of things happen. Okay, so now what happens? Now it's August last year, 2015. I'm talking to Ray. The book's basically finished, and I know that they're about to bring the advanced machine, advanced LIGO, online for its first science runs. And so I'm figuring I better wrap up the book because, they're wrapping up. What am I going to do, And Ray says, if we don't detect black holes, this thing is a failure. He just feels this weight, this weight. We've led the country down a garden path, $1 billion. It's the second generation of machines. If all we hear are things we already know exist, this thing is a failure. Black holes, that's what old-timers are after, he says. Pure space-time coalescence, pure darkness, pure gravity. And that's why I came up with the title Black Hole Blues, because I felt like there was this sort of, this heaviness that he felt in August. On September 14th, Ray, the weekend before, was in Livingston, in Louisiana, looking at radio interference and banging on the machine and interrupting it and giving it a hard time. He says, luckily, my wife told me I had to come home. So he gets on the plane, he goes to Maine. In the middle of the night, Sunday going into Monday early morning hours, they've already decided to postpone the science run because they just don't feel they're ready yet. They start interrupting the machine with all kinds of tests just to see how noisy they can make the brakes on a truck or how much they can interrupt the mirrors. And then finally, at something like 2 in the morning in Louisiana, maybe it's 4 in the morning in Louisiana, 2 in the morning in Hanford, Washington. On both sites, the scientists get exhausted, they're fed up, they put their tools down, they go home. Within the span of an hour, this gravitational wave that's been traveling for 1.3 billion years rings the machine first in Louisiana, coming from the southern sky. They get a beautiful recording. Skims across the continent, rings the machine in Hanford, Washington. By the time Ray wakes up, 8:30, something like that, Monday morning in Maine, he looks at the logs, which have automatically recorded this detection, and he says, what the hell is going on? What's that? By then, the gravitational wave is already billions of kilometers away. They spend the next several months literally freaking out. There's a lot of incredulity. They don't actually believe it's real. They can't believe it. They start accusing each other of putting in false detections. This goes on for a while. They literally interrogate their best people to see if anyone that they thought would be capable of doing such a thing had done such a thing. They finally realized that it would actually be impossible for anyone to pull off a farce like that, but it was something they took seriously. And within a few months, they made the announcement that you heard, which was on February 11th. So the announcement they made was that what they detected, and this is a computer simulation because we can't possibly see it with a telescope, we could only hear it with LIGO, 2 black holes, each one about 30 times the mass of the sun, in the final seconds of their orbits together, the final 1/5 of a second, were traveling about 1/7 the speed of light up to 1/2 the speed of light as they orbited each other. Each one's about 200 kilometers across, so they're going around each other hundreds of times a second. I want to see that again. That was nice. They let out the loudest gravitational wave train, collided and formed a bigger black hole about 60 times the mass of the sun. That single event was the most powerful event we've detected since the Big Bang. It emitted more power than all the power coming out of all the stars in the observable universe combined. And none of it came out as light. It all came out in this ringing of the drum of space-time. That was emitted when multi-celled organisms were fossilizing on the Earth. Right? By the time it reached some nearby nebula, Einstein was born and started theorizing about gravitational waves. When it was near Neptune, they were still hammering on the instruments. Right? And yet, within an hour, they detected this really spectacular event. So let's try to listen to it again. And that was also, by the way, drastically slowed down. You have to realize that these black holes could have been orbiting for 1 billion years. So that means in the first generation of instruments, the gravitational waves were washing over the Earth, but it was not sensitive enough to detect them yet. and they were quieter. It was only the final 1/5 of a second when it was loud enough that it could be recorded even by the advanced machine. And so we're going to hear, again, the raw sound, and then the slightly shifted in frequency, a little friendlier to the human ear. Again. And what you should be hearing is that really characteristic chirp of the black holes colliding and their final interaction. And then I just want to close. I thought, I don't have a, okay, I'm going to read from my book, if that's okay. I just thought I'd read the last part. So there have been 2 other detections since then that were announced, and both were black holes, black hole collisions. So it's really quite stunning that so far all they've recorded is black holes. And then I just want to read from the close of the book, and then we'll open it up to questions. There will be press releases, scientific papers will be published, news articles will abound. There will be documents, reports to the NSF, and careful records kept. We'll continue to send a portrait of our best selves into space, a declaration that we were here, that we strove for understanding, that we often failed and occasionally succeeded. We heard black holes collide. We'll point to where the sound might have come from to the best of our abilities, a swatch of space from an earlier epoch. Somewhere in the southern sky, pulling away from us with the expansion of the universe, the big black hole will roll along its own galaxy, dark and quiet, until something wanders past, an interstellar dust cloud or an errant star. After a few billion years, the host galaxy might collide with a neighbor, tossing the black hole around, maybe toward a supermassive black hole in a growing galactic center. Our star will die. The Milky Way will blend with Andromeda. The record of this discovery, along with the wreckage of our solar system, will eventually fall into black holes, as will everything else in the cosmos. The expanding space silent, and all the black holes will evaporate into oblivion near the end of time. Thank you.
My question is, how come the time stop in a black hole? So
Yeah.
the time stops, so there is no time in there.
Right.
What's the reason?
What is the reason?
Yeah.
Yeah, so I only talked about the curves in space because it's easier to think about that, but Einstein, before general relativity, described special relativity in 1905. Long before he thought about curved space-time, he just thought about space and time. And he thought, if I think about time, it's really another dimension. It's not an easy one to comprehend, but there's a sense in which we physically move forward in time. Like I could draw it on a board. Time is a direction, and we move forward in it. And space is a direction. The difference with space is that we can also move back. We don't know why we can't look back in time or move back in time. But once you do that, Einstein's whole theory of special relativity is basically the idea that you can rotate space into time. Let me give you an analogy. So let's say I say this is my left. Most of you will disagree that this is left. You understand it's a relative notion. You're not at all shocked that I call left something different than you call left. If we want to align our lefts, we simply rotate in space. Now I'm aligned with you. What Einstein realized is when things are moving at a certain speed, it's a rotation, it creates a rotation in space-time. So part of what I'm calling space becomes rotated into what I'm calling time. And we disagree fundamentally then. Just like you disagree, this is not fundamentally left. It's just not an absolute notion. So once you start including time in these pictures, which is very, very hard to do because we can't visualize 4D, you realize that things not only curve space, they also rotate space into time and time into space. As you get closer and closer to the black hole, what's basically happened is you've rotated so much that when you hit the event horizon, if I were an astronaut in the space station and I threw my compatriot into the black hole, it would look to me like his or her clock essentially stopped by the time they hit the event horizon. And that's because of this extreme rotation. It's as though I've rotated left 100% into right. Okay, so, I teach entire semesters of 2 semesters of classes on this. So, if you're getting it in 2 minutes, awesome. And I've worked very hard on thinking about it this way, right? So the other thing is that the astronaut falling across the event horizon thinks their clock is fine. Okay, their clock is fine, totally normal. They think you're going really fast. And so they cross the event horizon in a finite time. But you think it's taking forever. So by the time they cross the event horizon, you're gone. You're dead. Thousands of years have passed for you. but not for the astronaut. The astronaut, it's a fraction of a second. And so that's why when they fall into the black hole and they see the light from the galaxy fall behind them, it's like this rapid series. They could see civilizations come and go, stars die, because time is going much faster further away from the black hole. And this is a real effect. We can measure this with our GPS units, that our clocks go slower on the Earth than they do in the satellites that are farther away. And it's important enough that your phones have to be corrected for it, or you'd never be able to tell Uber what corner you were on.
Why do black holes combine instead of break? You know, when you think of throwing two particles together, they break and we find something on the inside, but
yeah.
Why black
It's
holes
a
just
very
combine?
interesting question on many levels. One answer is that a black hole is not a thing, despite what you've been taught. One way to form them is by crushing a star. But once the star creates that shadow, the material of the star continues to fall towards the center. It cannot stay where it is any more than it can travel faster than the speed of light. You can think of the space-time as almost being like a waterfall falling inward. And for the material not to fall, the space-time's actually draining out in some sense. It would be like trying to swim against the Niagara. So the star is gone. The material of the star is gone by the time the black hole is a quieted down object. So it's really like a place. It's a pure space-time object. It's just one of the most stunning things that we know about the universe. And because of the event horizon allows nothing to escape, there's nothing to break. There's no material there to break, and nothing can come out of it once it falls into it. So the only thing a black hole can do is get bigger. I mean, I'm barring Hawking radiation and evaporation, which is a whole other complex issue. But that doesn't happen for these big astrophysical black holes for the age of the universe. And the other question, which I think is really important, is you compared it to fundamental particles. We smash fundamental particles together. There's a sense in which black holes are like a fundamental gravitational particle. I'm happy to see, like, they're going for it. Go for it. Okay, oh my God, complete decay. Okay. Okay, I guess there are no more copies, that's all right. Well, I'm honored. I'm a little disappointed there wasn't a fist fight, but... So let me just say one more thing about your question is when they started the Large Hadron Collider that detected the Higgs particle, they smashed particles together and they thought they might make black holes. And there was an injunction against them because people were afraid it would destroy the Earth. They did neither make black holes nor destroy the Earth.
So in the beginning of the book, you chose to write a lot about Ray and to include a lot of like pure text from the interview. Why did you decide to do that?
Yeah, that's a nice question because I set out to write a completely different book. I wanted to write a book that was just straightforward about black holes, you know, a much more kind of regular popular science book. And I became so enamored and they were friends of mine too. I didn't know Ray, but I knew Kip very well and a lot of the experimentalists. But something about Ray's lexicon and the rhythm of his speech, and I would be listening to him while he was taking me around the experiment. And I was thinking, you know, Ray's a character in a novel as much as anything, and that these themes are sort of, you know, they're universal themes: ambition and failure, and doubt, and personality conflicts, and this desire to climb the mountain and not knowing if you're going to succeed. And so I decided to write the book as much like a novel as possible, and that meant dialogue. And it was just a gift that I actually had dialogue. Now, what you see, I mean, I have hours and hours and hours of tape with Ray. And so it's drastically pared down. So what I really wanted to get was the honesty of his voice, and he read it. I happened to print a copy of the book on September 14th, the day the gravitational wave hit. And I sent it to Ray. I sent a copy to Ray and a copy to Kip. And so they read it very, very thoroughly, and we went over every date and every, you know, and they were such scientists about it. There were some things that they didn't like, but they're, like Ray would be like, oh, I don't like it, but it's true. You have to leave it in. I don't like it, but leave it in, you know. And they were just so honest to the last. Nobody told me to take something out that was unflattering or that they didn't like. But he also couldn't stand not telling me about the detection. So they did tell me early. He said, I know you want to write an epilogue if there's a detection. And so I got a note, a lovely note from the director of LIGO and from Kip and Ray. So that was really, really a great honor. But I guess the point was that it was supposed to read like a novel, as much as I could. Thank you all for coming. I'm really honored you were here. It meant a lot to me.